Good morning, everybody. Today we are going to start our new chapter with new unit, that is influence lines. What is influence lines and why we are using these influence lines? As we know that all the buildings that we are designing, that is for the static load, dead load and live load. But in some of the structures, they are having moving load, and that moving load will gives us the shear force and bending moment diagram, which is not in the same as static, because whenever the load moving from support to span and span to support, it will create a fluctuation in a bending moment diagram. So for that fluctuation of bending moment diagram, and from that fluctuation we want maximum shear force and maximum bending moment for the moving load, it will done by the influence lines. So what is influence line? An influence for any given point or a section of a structure is a curve or graph whose ordinate represent to scale the variation of a function such as shear force, bending moment, reactions at support, deflection, etc. at a point or a section as a unit load moves across the structure. As I said, it's not constant, it is fluctuate from point to point. Now, what is the importance of influence line diagram? In a practice, structure are subjected to dead load, live load, as we discussed. Dead load due to self-weight of the structure, finishing wall, partition, etc. Loads like a human load, furniture, vehicle, etc., which are not fixed in position, term as a live load. Live load which causes vibrations in a structure such as moving vehicle on highway bridges. So it is most important for the bridge analysis. Moving crane, which is in industry, etc., are called impact loads. The influence lines are very useful in a speedy determination of the value of a function at a given section under any complex system of loading. It is not proper, it is complex. So from where we are going to finding out the reactions for the moving load, and that is, let's try to understand that this is our simple span of one of the bridge, and the moving load is acting on it, and that load is considered as a unit load. This unit load moving from A to B support and having a length L. So reaction at A, that is unit load 1 into L minus Y upon total length, and B is equal to 1 into Y upon L. Right? This is the Y distance, and it is not fixed, it is somewhere on the whole span. So influence line for RA, when Y is equal to 0, RA is maximum, and Y is equal to L, at that time RA is 0. So the diagram for influence line due to RA, and that is 1 over here and 0 over here, so it is inclined line. Same thing at B, when load is at point B, then reaction maximum over here, and here it is 0, so it is again inclined from 0 to 1. So this is for the reaction. Now same thing for a shear force. In this case, the VC, the reaction over here, that is RB, and that is minus y upon L, right. Same thing at C, y is equal to x when x is at a C point. So the load is moving from here to here, and what will happen? Vc is equal to minus x upon L. This is a reaction at A, at C, and again from right to left we are considering that, then reaction is equal to L minus x upon L over here. The summation of these two, that is 1, and the load when acting at C point, it is perfectly 1 unit load. So we can consider our diagram like this. This is RA and this is RB. So at C point it will be create the shear force like this one. Now influence line for bending moment. We know that the maximum bending moment due to point load, that is WL by 4, right, and whenever it is not at center, so WAB by L, so we can consider this is X as A and this is as B, so WAB by L, and W is unit load, so it is X upon L into L minus X, maximum bending moment over here. So from this diagram we can calculate the maximum bending moment in sum of the point at C. If this C is the fluctuate and not constant, so whenever we are going to finding out the maximum bending moment, we can consider X, and when we are going to changes this X, we will get maximum bending moment for the influence of the load. So this kind of bending moment diagram from the influence line we can plot. Now from this, the load position for a maximum shear force at a section, what we are going to consider, as we know that if the unit load at C, it is maximum in minus as well as maximum in plus direction, and the whole the summation of these two, that is 1. So whenever it is in a left hand side, then it is a minus x upon L, and when it is a plus side of the unit load, that is L minus x upon L. So from this we can get the maximum shear force for a particular point, and from this diagram we can calculate the whole influence line, and that influence line can generate anywhere of the structure, so we can calculate basis on that. Now if we are going to consider UDL for a longer span, then from the influence line of shear force at C, it is clear that the maximum negative shear force will occur in a span AC, that we know, and loaded and span CB is empty. Now Vc is equal to maximum negative, that we know left hand side, that is negative. So minus W into area of influence line diagram under the UDL, and that is minus W into 1 by 2 into x upon L. So it is Wx square upon 2L, and the shear force will occur in CB part, that is positive, and that is again W into 1 by 2 L minus x into L minus x upon L. So it is W L minus x square upon 2L. These two value gives us the shear force maximum for the UDL cases. When UDL in a shorter than span, then it create the A is less than L, then it will gives us the different position, like the same as we discussed. Several points load, the maximum shear force at C. Suppose this is the number of point load. Consider a suppose a train is moving on the bridge of the railway, then the point load due to all wheels of the train is something like this, and the distance between that two wheels are always fixed for a particular one coach. So whenever we are going to finding out the maximum shear force at C. Let us the first W1 will be the section at C, and let us under the load W2 at the D behind it. This is W1, W2, W3 and W4. So the deflection delta is given by the WD upon L minus W into 1. Now it will change the shear force diagram, that is delta Vc, and W is equal to sum of all the point load, and D is the distance between loads at C and for the next load. Now L is equal to span of the beam. If the delta Vc is positive, the rolling will be increasing the negative shear force. In such a case, rolling must be the continue till delta Vc become negative. Thus, the load position will gives us the delta Vc will be the correct position of the load to get maximum negative shear force at C. Now, maximum positive shear force is, to get the maximum positive shear force at C, let be the last load W4 will be the section at C, let under the load W3 be a distance ahead W4. If the loads are moved by distance D to the left so that W3 comes over C, the change of delta Fc is given by the delta Vc is equal to Wd upon L minus W4. If delta Hc is positive, the rolling to the left will increase the positive shear force. In such a case, rolling must be continued till delta Vc become a negative. Thus, the load position which gives the negative delta Vc will be the correct position of the load to get maximum positive shear force at C. So, from this we can calculate for the UDL maximum position of shear force and maximum position of left and right, means it is positive and negative. Now, the load position for the maximum bending moment at section. Suppose this is a single point load. Let a single point load W roll from left to right. The maximum bending moment C will occur when the load is just at C. Now, this is our span AB, point load over here, and it is a distance Y from left support. The C is at the x distance and C to B, that is L minus x. Now, as we discussed, the maximum bending moment at point C, it is WAB by L, and this x is considered as and this is as B. So, what is done over here? This is our maximum bending moment diagram, WAB by L. This is our point C. So, at C it is maximum, as we can consider this unit load at point C. Now, maximum moment at C is equal to Wx into L minus x. When UDL longer than the span, then the MC is maximum W into area of influence line diagram, that is W into 1/2 of L into x upon L into L minus x. So, it is Wx square by 2 into L minus x. This equation gives us the maximum bending moment for the UDL. When UDL is shorter than span, something like this, then we have to consider these two positions and take the average value of this diagram will gives us the maximum bending moment. So, let the UDL length A roll from left to right, which is less than L. For the maximum bending moment at C, UDL must be so placed over beam the ordinates AA1 and BB1 are equal. The maximum under UDL will obtain only if the AA1 is equal to BB1. For AA1 is equal to BB1, for the following condition must be satisfied. AC upon CB is equal to AC1 upon CB1. Now several point loads, WL upon X minus WR is our L upon X. This is our equation where W1 resultant load from the left of the section C and WR is equal to resultant of the load from right of section C. Now the position and amount of maximum bending moment for several point loads. These are the number of point loads, and for the maximum, what we are going to do, we have to take diagram at C, and that is X upon L, that we know, and here the ordinates for this, that is for W3 it is Y3, for W4 it is Y4, W1 Y1 and W2 at Y2. So from this we can calculate the maximum position. For the designing of the beam, the absolute maximum bending moment occurring anywhere in the beam should be found out. If the span of the beam is very large, we may assume that the absolute maximum bending moment occur at the center of the beam. However, for the support span beam, it is not true. Whenever the span is short, right, it is not happen, it can be changed. It is thus necessary to determine the position where the bending moment maximum occur. But when it is a large, then we can consider it at a center. Now the position when a series of wheel load crosses a girder, means on a beam, simply supported at the ends, the maximum bending moment under any given wheel load occur when the center of the span is midway between the CG of the load system and the wheel load under the consideration. In the figure, the center of the span is midway between the resultant of R and the wheel load W3. This arrangement will gives us the maximum bending moment below point load W3, that is Y3. Another wheel load can just chosen and the procedure repeated get under the value of maximum bending moment. 2 or 3 such series may sometimes needed to be a absolute bending moment will be the greatest of these. Now position and amount of maximum shear force for the several point load. Place first W1, W2, W3 as like that. In that case we are choosing W1 at B. Find out the maximum delta VC, that is WD upon L into W1. If the value of delta VC is positive, place the second W2 at B, means it is moving from here to here, here to here, where the P is the point load leaving the girders. ये ऐसे ऐसे आगे बढ़ता चला जाएगा because it is moving. The load placed at B, which gives the value of delta VC, that is negative, is the critical load. This critical load placed at B will give the maximum shear force at B, that is RB. Similarly, place the last load W4 at A and find the value of delta VC. The value of delta C is negative. W4 is the critical load for the load. It should be placed at A, finding out the maximum shear force at A. If the W4 at A gives the positive value delta VC, try to load W3. Right? Means whenever it will going to negative side, that is maximum. Thus the maximum shear force occur at either A and B. So these are the cases, and from the basis of this we can finding out the how to calculate the maximum shear force for the moving load and maximum bending moment for the moving load, in which case it create a maximum and where it is the point at which it create negative and positive. From that we can design the whole span of the bridge and span of the crane girder that is generally used in industrial building. So from the basis of this influence line we can design the whole span of the bridge. So dear student, this influence line diagram is for the determinate beam, and for the indeterminate beam it will be discussed by me in a next lecture. So you have to go through this whole theory portion, and we will understand how to find out the maximum shear force and bending moment for our moving load. Thank you very much.